Okay, so this is Chapter 3 Notes, and we're starting with Section 1. And we're just going to go through an introduction of exponential functions. So generally, exponential functions take this form, where we have some base here, and then our variable is now in the exponent. So our variable is in the exponent, and then the bottom number here, this b value, is called our base. Now the b value cannot equal 1, and it must be greater than 0. These are just some examples of exponential functions. So sometimes, actually this one right here is x should be in the exponent here. So this should be x squared, or 2x, like that. And this is an exponential function. All of these are variable is in the exponent. These are not exponential functions. We can't have a -1 here, or a negative value at all. We can't have our variable in the base. We can't have 1 as our base. We said b could not equal 1. And then our variable shouldn't be down here. It should be in the exponent. So let's go ahead and just kind of explore what these graphs look like. And when we first learn a new graph, generally what we do is we make a table of points. And that's what we're going to do here. And I'm going to start from -3, -2, -1, 0, 1, 2, and 3. We'll plug in those values. Now, I'm going to start with the positive values just because they're a little bit easier. 2 to the third power is 8. 2 to the second power is 4. 2 to the first power is 2. 2 to the 0 power is 1. 2 to the -1 power. Well, that's 1 over 2 to the first power, and that would be 1/2. Well, then 1 over 2 squared is 1 over 4. And then this will be 1 over 8. So we can kind of see what's happening here. We end up with the reciprocals of these values. So looking at what we have so far, we can go ahead and plot these points. Starting with x equals 3, I have 1, 2, 3, 4, 5, 6, 7, 8. And then x equals 2 was 1, 2, 3, 4. X equals 1 was 2, 0 was 1, and then -1 was 1/2, and 1/4, and 1/8. And if we continued to plug in larger and larger negative values, let's say -1000, it still wouldn't equal 0, but it'd keep getting closer and closer and closer. Now, what we have here is called a horizontal asymptote, and that horizontal asymptote is at the x-axis here. Typically, I'll write my asymptotes in highlighter just to show that they aren't part of the graph, but it is approaching that value, and you do need to graph your asymptote. Now, if I keep plugging in bigger and bigger values this way, my function is going to shoot off to infinity and get really, really large. This is a growth. This exponential function. It's growing. As we move from left to right, or as our x values are increasing, our function is increasing. Okay, so as x increases, f of x increases. Okay. Now let's look at the next example here. We have 1/2 x, and we're going to see something else happen. So I'm going to use the same x values, -3, -2, -1, 0, 1, 2, and 3. And when I plug in these values, let's say I plug in 3. 1/2 to the third power is 1 over 8. 2 gives me 1 over 4. 1/2, 1. I'm plugging in a -1. Well, let's just do this off to the side here. 1/2 to the -1 power flips this, and I have 2 over 1 to the +1 power, and that's 2. So kind of like what we saw before, we end up with the reciprocals. Okay. Well, now we can go ahead and plot those points now that we have them. -3 was 8. -2 was 4. -1 was 2. 1, 1/2, 1/4, 1/8. And again, we end up with this horizontal asymptote. And this is a decay. So as x is increasing, or as we move from left to right, our x is increasing, our function is decreasing. Okay. So that's just kind of an introduction to these graphs, and we can kind of see the difference here. Notice that my base here is bigger than 1. My base here is between 0 and 1. We'll notice that that's a pattern with growth and decay functions. Your decay is already going to be between 0 and 1, or your exponent will have a negative on it. And up here, this should be positive and this should be positive, or if they're both negative, or I'm sorry, if this is between 0 and 1 and this is negative, then it'll end up being a growth. Let's go ahead and move to the next page, and we can look at some more information that we have here. Now, I'm going to use a few different color highlighters here to model these functions here. I have f of x equals 2x, and that's going to be this graph right here. I have g of x is 7x, and that's this graph right here. I have h of x is 1/2 x. That's this one right here. And then we have j of x, which is this one right here. And if you just take a second and look at how these different bases affect our graph here. If I have a base that's greater than 1, this 2 and the 7 here, then it's getting steeper and steeper. 2 is this blue line, but when it increased to 7, it got that much steeper. And then it also shrinks faster this way. Notice that the orange is below the blue. And something similar happens with our decays. 1/2 is this green line here. It's a little bit flatter, but the closer it gets to 1, it gets steeper and steeper. Now we've generalized some of the shifts that happen with these graphs below here, and it's very similar to what we saw in chapter 1 with shifting all of our graphs up, down, left, right, and stretching and shrinking and all of that. So this should be very familiar to you. Adding and subtracting a value on the end changes it vertically. Inside the exponent here changes it horizontally, and it's opposite of what we would think. So if it's a plus, it's left. If it's a minus, it's right, and vice versa for the vertical shift. The reflection, if we have a negative out front, it reflects across the x-axis. Inside the y-axis, we can stretch or shrink it with a value out front and stretch or shrink it horizontally with a value inside the exponent. So that should all be familiar. Now, looking at the bottom of this page, it says the natural base e. In calculus, you will almost always use e. You're not going to use other bases very much. Same thing with logarithms. You're not going to use regular logs. You're going to use natural log. So this is something you want to make sure that you're getting familiar with. So the natural exponential function here, that's e to a power of x. Okay. Again, I'm going to go ahead and flip the page here. And we've got a bunch of examples to graph here. Now, because I don't think I can fit all of this in one video, I'm going to go ahead and stop it here, and then we'll pick up with part 2, where I'll complete all of these graphs.